Good evening, Jai Kumar. Okay, we have around 30 people, 31, 30. We just wait for another 1 minute.
Okay, as you say.
Okay. Okay, so I think we can start. I welcome Parmeshwaran sir again to continue his talk. So today we'll be covering TMTC communication.
In general, I'll continue with that the part of the series and why the TMTC all required and all those things. I can touch upon that.
Okay. Fine, sir. We'll start.
Okay.
Yeah.
Am I audible
Yes.
properly?
Yes.
Okay. So then I will go into the presentation mode.
Okay.
Just configure my slides. Are you able to see?
Yes.
Okay. And good evening to everybody. Guru Bhyo Namaha. And salutation to Guruji and my gurus. And thanks again for rejoining the session. And I would like to continue from where I have stopped. I was discussing the day before yesterday on the aspects of the satellite designs, how the size and the shape, the how strong, that is rigid or flexible, and depending on the mass and mass distribution. And I was just trying to recap whatever we have discussed, and then I was trying to illustrate to you the need for the why we need to control this satellite, why it cannot be just left in space to do its intended function, or what the kind of disturbances that what we are trying to experience, and how are we going to have affected by that. So this is what we have discussed, and also I just given you some glimpse of the different sensors, like whatever the sun sensors, and then the infrared sensors, that is the earth sensors and the star sensors, and some of them are the magnetic, that magnetometers. And we just discussed about some electromechanical sensors like gyroscopes, and then the actuators, where either it could be a thrusters or it could be a reaction wheel. And someone asked me what is a reaction wheel. I just was trying to explain to them it is a motor connected with the mass spinning at some particular speed. So we will be able to control the speed of the motor, through which that we will be able to control the momentum. So, and also, see, generally, instrumentation people they would be already been familiar with some of those measurement gauges, like which, like for example, that you would like to make a measurement of the temperature. So you will have that either the thermistors connected in a bridge network, and then that depending on the change in the resistance, the null point is going to change, that you can monitor, and then you say that whether how much is the temperature. Or if you are trying to monitor the higher temperatures, you can use a thermocouple and things like that. And then there are so many sensors which you will be in a real life, what we will be having is something like a flow meter. Suppose if there is a fluid which is passing through a tube, and the amount of rotation that that meter is trying to make, you will be able to do that. And especially when it comes to this the reaction wheel, when we are talking about the motor speed. So some of the people, those electrical engineering people, or even any one of those instrumentation people, you would have come across what is called the tachometer. The tachometer is the one which just measures the speed of the rotating object, that in this case the motor, how much is the spindle it is using. How do you implement this kind of see? And then like for example, before that, suppose you have a optical sensor, like for example, that you pass a light, and the number of times that the light is cut, and then now if you pass through, you put a rotating wheel in front of that with a kind of mask. So how much is the rotating wheel it is doing? So how often that you get the open and close? Suppose if you are able to measure that, then you will be able to know that there is some amount of how fast that moving the rotating object is there. So whatever we normally face in our instrumentation kind of thing. So it is some amount of similar uh, gauges are being employed in the satellite field also. And because initially they were all having this kind of, the principle remained the same, but how you implement it. See, because of the technology, what we are having is that we are having going through what is called a miniaturization field. That suppose what would have been a mechanical sensor, now people would be implementing that same principle using what is called the MEMS, the microelectronic thing. So it is a miniaturization. The principle remains same. So there could be another, like you might have come across what is called a Hall effect sensor. There is piezoelectric. That is, if you apply uh, electric voltage, and then some of the materials will have the vibrations and things like that. And the reverse is also, if you try to apply a mechanical force onto that kind of a material, it will generate electric response. So you can just calibrate this kind of thing. So we know that whether it is whether it's the pressure you are trying to measure, and this kind of sensors, you whatever you normally feel in your normal day-to-day life, and also more things you have seen in the laboratories. So the similar principle is being applied. That is what it is being carried forward, but due to various reasons, some big names have been given to them. And then because traditionally these are all the things, because finally they like, for example, if somebody will say it is a flow meter. What is the flow? See, what is it is giving that it is just trying to measure through a kind of a rotating wheel, that how much is the fluid, that what is passing through that. So you would like to know that, suppose if you have carried 1 liter of fluid into the satellite, how much you have spent, so that you may have to make a measurement of it. Then that is, so then, for example, some other place that you would like, it is a closed volume. It is like one of the pictures I was shown, that there is a sphere. And in the sphere, that you have put in some amount of liquid and then pressurized with some gas. So you have no other way of knowing that how much is the mass that which is sitting there. Suppose if you are trying to take out some of the mass in this thing, change in the, see, you have volume remains same. And if you monitor the pressure, if you are putting a pressure sensor, and if you are having a temperature sensor, using that PV equal to RT formula, you will come to know that what is that, one of the things, what is the volume of the fluid which is sitting there inside. So we come to know through various means that these are all the things that are happening on the spacecraft. Essentially, some of these sensors are giving you ability to know where you are. Some of the things are trying to measure what is happening inside the spacecraft. Say, for example, some part of the spacecraft, whether it is experiencing the high temperature or low temperature, you will come to know. If you instrument that particular area, what I mean by instrument is that you take a thermistor and put a adhesive and stick it onto that wire, you bring it to some bridge circuit, and you use it in that electronic circuit. You will know that what is the, at that particular area, what type of temperature it is going through. So this is what we call instrument. You instrument the spacecraft in such a way where you need temperature monitoring, where you will, suppose, say, for example, if you want to measure how much is the current that it is passing through. The current passing through, you put a standard resistor, so you know the voltage across the resistor, that how much voltage it is happening. That voltage you can always monitor and calibrate it and say that this is the current that is flowing through that particular circuit. So, like these kind of things, there is in the spacecraft, there are so many things that you can be able to monitor. But how do you bring it to the ground? So that is what we call that. It is you see all these instruments. You can say that it is all, you are able to see what is happening on the spacecraft, or you are able to feel what is happening. But that is what, when you bring it over through that some means to the ground, we call it as a telemetry. That means a telemetering. That means you are able to measure those kind of things sitting in your control center, what is happening onto the spacecraft. So that is what we call, if you bring it in the, see, and certain things that when I said in the first of my slide, which is digitalization. When you have the digitalization, what it considers, many of those people, we are talking about, let us say that I'm trying to monitor the temperature. The physics tells that temperature of any body, it doesn't change so drastically. Okay, it just varies slowly, and depending on the heat input that is coming or the heat loss that is taking place. So I need to monitor at certain intervals. If I know what is happening with respect to that particular temperature sensor, I call it as a thermistor. Okay, if there is a thermal resistance, it is called thermistor. So if I know that, see how often I should put, maybe once in 15 minutes or once in 5 minutes, if I know what is happening. So that if I know the data, if assuming that these are all the kind of, and this is a, in computer science people will say that whenever that they would have used the expression or they would have used the programming, say that you have so many ports through which data is available to you. So you scan those ports. What is the way that it is having? In this port, what activity it is sitting there? It is something similar to that. So you scan the particular measurement area. That means you scan means you look for the data particular time frame. So that time frame, it is, you get the data and then use it. And but there are certain things like, for example, you are trying to see that the rotation of the spacecraft. Like for example, you want to monitor the speed of the motor. The speed of the motor, you have to know every, suppose it is rotating at 1000 rpm or something like that. That means every second it is going to have some value. So that means you need to monitor at more interval than what you are trying to monitor on the thermistor stem. Similarly, with respect to what the array, how much power it is generating, you want to. So you need to know voltage and you need to have the current, so you can draw that particular. So in this kind of a group of info data, some data is varying fast, some data is varying slow. So the principle behind is that what is called a sampling thing comes into picture. The sampling, you would have all studied about the sampling theorem. It says that if whatever the highest frequency which is happening, if you double the rate of the sampling, you will be able to know more or less accurately that particular change in the variation, or you're able to see. So these kind of things are, suppose, like for example, and the computer science people would have studied about the data packets. So I say that, like wheels, I want to know the motor speed. And that motor speed, it could be like, for example, I just want to know how many RPM it is going through. So I associate either a 8-bit word or a 16. So I that bit, so many bits are coming. So let us assume that like this voltage, I have another 8-bit information that is coming. A current, another 8-bit is coming. So these are all what is called the different words of data which is coming. Suppose if I sequence it all together, so what, like I will have a data stream. So that data stream, if put together all those things, let us say I start with the wheel speed, go to the like a voltage, then I look at current, then I look at temperature, then I look at, let us say, for example, whether I have sun sensor data, which is whether the sun is present or not. Same way, earth sensor data, earth is present or not. See, this kind of it. So once again, I complete that cycle and then come back to the our motor speed. That means one cycle is that. So the one stream of data, we call it as, let us say, it is a one particular frame of data. The frame of data, depending on whatever you are having, it can be either you decide how many bits you want. It could be like, for example, 1024 bits, or it could be like, for example, 512 bits, or it could be 128 bits. And each bit, either you want to call it as 8-bit as a one word or 16-bit as a one word, whatever you want. So many words of data. So this is arranged in one particular frame. So this frame gets repeated from this particular telemetry. So then what you have is that you have a telemetry stream which is coming, it is available to you. So either you have options, two options. Either you can store, if you have a memory on board, you can store this data very sequentially on that particular, you can start writing in a particular memory area. And then later on, when you have, like yesterday, you would have seen that when you are having the visibility to the earth station, you may downlink the data. One of the downlinking the data, you can start scanning this memory region. So you will get the telemetry which is coming through that particular word. So you get to know. But then suppose if you are continuously varying, suppose real time you wanted to have. So then what will happen is that, as many of those people would have said that, so depending on the clock speed, what you are having on board, you can design that data stream. But each pack, let's say that starting point and then ending point of one frame, and then next starting point and ending point, then you want to have some amount of synchronization. So you use the ground, let's say for example, you are trying to process. See, for the ground processing, everything looks ones and zeros. You don't know what it is, whether it is corresponding to uh, uh, whether it is motor speed or whether it is corresponding to a temperature data or the current data, you do not know. So what you should do, you should provide the timing. So you should know what is the frame structure, what is it. So for that, what we need is we assign certain bit streams in the beginning or the end, what you call identification markers. See here, some people call it as a frame sync. Either it could appear in the beginning or it could be appearing in the end of the data stream. So depending on what protocol that you are trying to use it, you have that particular system. So many bits, a standard pattern. Let us assume that something like some 10 zeros and followed by 20 ones, and you decide whatever that pattern, even if all the satellite systems are all switched off, even if it is nothing, is that this only telemetry is alive like that. So then what happens, this is the pattern which will come with, let us assume all other instruments are off, it is supposed to give you 0 0 0 0. So this particular stream is in any given frame, this particular data pattern is going to appear. This is what is called a frame sync particularly. So this telemetry data, whatever your data what you are generating on board, you can either have a concept called store and forward, or you can have a real time coming to you. So this is about what is happening on that spacecraft telemetry. It depends on how you organize. See how often it is, how much you want. Certain times, like for example, sometimes it is like in some of the people, like science people, would like to know something under the microscope. What I say, to know more structure on that particular object, whatever your sample is at. Like that, see, for example, I just want, I have designed, let us assume that every 1 second I look at the wheel speed data, or every 1 second I look at the sensor data, sun sensor data. But I know that something is happening, suddenly something is happening somewhere in the spacecraft. Let us say my temperature, for some reason the temperature is shooting up. See, though I have given the temperature data to be coming once in 5 minutes, now my interest has changed. So I want to look at the temperature more often. Like for example, every 1 second I want to look at it. Maybe you can program through your command and data handling subsystem. You can provide an option so to say that this particular format has to be changed to look more often into this particular. I may look at only temperature. That means I will have what standard format is. Oh my, there should be one header. That means identification, frame sync, identification pattern, followed by all those real-time data depending on. Now, what my interest is to having only one particular data point look more often. So then what happens now? I construct a stream which says that which is having only that frame sync, followed by, let us say, I always look at that temperature data. That 8-bit means that temperature, the 8-bit data, temperature, like that. I fill up, let us assume that I remaining 128 bits. Let us assume that 128 and the header is having another, let's say 20 bits. So total 148 bits will have, except the remove the 20 bits. So 128 bits will be looking at only at that particular parameter or a group of parameter you can decide. Instead of looking at all entire parameter, you can have this. So this kind of flexibility you can build this on this command and data handling system. So then I said that inadvertently I've used one word called command and data handling system. What is that command? So now I have the requirement that I have already designed a certain normal parameter. From that, now I want to go into a special parameter. I have to change. See, that means I have to provide an instruction. So that instruction is called the telecom. That means I'm remotely changing the mode of the operation of the spacecraft. So I have to send certain instruction, that is the command. So the command, again, is a particular sequence of bits which will be recognized by that satellite as if that there is a command coming from the ground. So I need to change the structure in this way. You would have been already programmed. Once you see this instruction, then you have to get into the different subroutines of this particular operation. So that much is already pre-designed. So this particular code that comes here, so in this case, like this, like for example, your payload will be operating, let us say, in mode 1 mode. I want to change the different mode of operation. So again, that for example, for mode A to mode B, there will be a sequence of codes which is this. If I send this code, then this command and data handling system will interact with the payload system, which will say that change from mode A to mode B operation. Now I have, this is what is the set of sequence. This is like instruction set of your microprocessor or microcontroller or this is once the satellite is designed, the satellite is designed with the telemetric format and as well as the telecommand format. That means these are all the final. See, it does, as long as you are in ground, you can have any amount of, you can touch that this thing, but once it is designed and closed in this thing, your access to satellite is only through this kind of instruction set. These instruction sets and the response to those instructions is only coming through this particular format. Now you have to manage. This is the where the telemetry telecommand interface is sitting there. It's a TMTC. So all these sensors and other things, finally what you, wherever they are located, you observe this electrical output in and try to, even though it is maybe analog or mechanical or anything like that, you have to now bring into what is called the amenable electrical form. So electrically, when you say it is nothing but bits and I think on the ground you have a corresponding table which will say that if I see a pattern of 10001, what does it correspond to? It may correspond to 5 volts. If I see a pattern of 01023, 010101, something like that, so the wheel speed is corresponding to 1000 rpm. So that means you have to have a calibration table on the ground. You have to have the processing that we may have a display on the your console. So this is how that your interface between the telemetry, telecommand, and all those things are happening with respect to it. So whatever this is where when you design this kind of thing, what is involved is instrumentation people have to be involved, and then you have to have the protocol. That is what is the kind of data interface that what you can have, and how you often there is what is the, how do you interact with that thing. So you need to have that algorithms developed, and that is how, if you put everything together, it can be implemented in hard way, in the sense discrete components or the thing, whatever you let us say, assuming that even if you are putting it on a FPGA and even if you are putting it in a standard the digital circuits, so you can have that thing simplified, you start with it. But if you want to have flexibility, then people will try to put it in a FPGA, and further they will try to put it into as a computer. If instrumentation amplifier can be now made into a what is called application specific integrated circuit, ASICs. So you have analog ASICs, you have digital ASICs, you have FPGAs, and you have FPGA programming, and or any other put together, you can just have a single C. And further, you can have what is called a single purpose board computer separately for this kind of handling this payload data or handling this telemetry telecommand. You can have on single board. So now you can have you can take a general purpose board and start doing your own application on that. So this much port I will connect it to analog, digital, everything, whatever you do, as your science project or any of your student project, you would have done that. The similar things you have to now do it. Only thing is maybe there are some issues with respect to the what is the kind of protocols to be followed. That probably my next speaker may tell you, and I will also maybe slightly touch upon that particular kind of. So now this is where we are just introducing you to the concept of telemetry, telecommand, data handling, and such kind of things. This is where that is. Okay. You have any questions, please, at this point? Can I move on?
Yes, sir.
Okay. So now coming back to the other aspects of it, this is the way I have designed the spacecraft. Now let us say that like whatever our JNANAM project is going to be there. Let us say at some specific uh, location, I need to downlink the data. That means I need to access the data from the satellite and make use of it. So for some reason, for a typical reason, I just taken, see, the satellite is going through the or in orbit this there, but I'm taking a top view. Let us say I'm looking at from the North Pole, how it will be looking. Whatever be the plane of the orbit, it is satellite is, let us say, it is trying to go through that. And I have put, for some reason, I have put the sun here. See, at this point of time, let us say at some point identified as a T not one, the spacecraft they should be in this direction, and at some point that not two, the spacecraft should be like this. At the point P not two, spacecraft should be like this, and
Okay.
again, pardon me. Okay.
Excuse me, sir.
Huh.
Slides are not changing.
Signs are not changing.
Yeah.
Am I see? This is now okay. Can you change it up?
No. No.
Okay, I'll just get out and then I'll come back again.
Okay.
I'll stop presenting and then once again I'll come back.
Okay.
You're able to see now?
Not yet.
The white slide.
No, sir.
Okay, I will probably I will rejoin the meet again. Give me a minute. I will restart the whole process.
You can select the entire
I have done
screen.
that. Maybe it
Entire
is
screen.
somewhere it is hanging.
Okay, fine.
Okay, it is just hanging somewhere. Let me just see.
Okay, fine, sir. You can log out.
This is the problem. Bandwidth problem.
Okay.
Am I able to see?
Yes.
Okay, that means somewhere it hung up. Okay, I was in this. We were talking about that all the telemetry, TMTC on this particular. So now I just wanted to go on to this slide. It says that I just taken a snapshot at how the satellite will be in motion, and let's say at some point of time specified by the designers that so I just coded as a T001, and the spacecraft orientation should be like this. That means the velocity vector should be like this, and then some part of this one, this green arrow, whichever corresponding to on the satellite. So it should be on this particular orientation. At this point of time, at 002, it should be like this. Similarly, on 3 and then 4. This is the requirement which is being specified by the designer or the mission designers. I want to have that. So how do I achieve that? See, and you see, you would have, see on the spacecraft, let us say, assume that you have certain mechanism, you have stored all the data, let us say telemetry and even payload data, everything is stored there. But now I have to interact with this kind of a thing. And if the satellite is trying to move in this particular orbit, okay, that is what it is, but that is orbital motion. But like for example, which I am able to communicate, let's say for example the antenna on this spacecraft is having this kind of overhead because it doesn't have the infinite field of view. It has got a limited field of view. So at some point of time the earth will start seeing it. And at this case, for example, here in this case, what the time instant noted as 01, it doesn't interact. And time in 02, it's slightly having a grazing incidence. Time 03, it's okay within the field of view, and time 04, it is within that well within its field of view. So I will be able to downlink, or I will be able to communicate. I will be able to send any command to the satellite also. So this is just, I am not taking any advantage of the any other, because my capability of rotating the spacecraft I am not using. I am only using the orbital motion to give you that kind of a connectivity where whichever the direction there. Suppose for some reason that this your requirement is satisfied at this way, you don't have to do anything. But Now, let us assume that there is a special event has taken place. You have payload has taken an observation. Let us say something which is, it has is a matter of interest, and then which you would like to immediately get to know what is that interest. So, at some point, let's say that I cannot wait till that particular natural thing. I want to make a movement. So, what happens in this particular in the thing? We say that if you are able to provide a rotation to the satellite, then what happens that I will have the connectivity from, let us say, I will get from point 02204, and then the other side I will have an extended continuity with respect to the satellite. So that is possible only when I have some kind of a rotation which is coming on it. So if the disturbing forces, if I leave it like that, it is naturally it is going to disturb and it is going to rotate to me. But there will be some occasion I necessarily have to rotate to meet my mission goal. So that is a requirement that it is coming into that. See, other than that orbital motion, I need to take something in this way also. That means there is a requirement that is coming onto the satellite. So if that, what if I summarize, if I leave the spacecraft in its space environment, because of disturbance forces, my orientation is going to get disturbed, and I need to do something to have the permanent orientation, desired orientation. At many a times, my desired orientation itself is not constant. It is likely to change depending on whatever the sequences that are happening on the mission time. So there are two requirements which are coming in that. How do I achieve that? So generally, this is where how do you? It depends on how you are stabilizing your spacecraft. See, if you stabilize your spacecraft in such a way that you are able to quickly move to the desired direction, whichever day you want it. So then it becomes what we call it as it is an agile spacecraft. Wherever you want, you can tilt and then take the it is agile spacecraft. It is something like, for example, a fighter aircraft. It is designed to do a lot of maneuvers, but at the same type of maneuvers you cannot do it on a passenger aircraft. A passenger aircraft, it is expected to fly in normal, very quiet environment. You would have seen last week there are so much of turbulence and people got injured and things like that. So in this, both are aircrafts, but the requirements, what is happening is, one is designed to be unstable, that because unless it is designed to be unstable, I cannot do a maneuvering. If other one is designed to be stable, that's why I need to have the passenger comfort and things like that. So this is the kind of different contrasting requirement that comes onto this control system or the spacecraft, which depend. That is a mission sequence. At what point of time, what way you need to do that, that has to be properly designed. Because when you are talking about management of the space asset, you have to written down these are all these thing requirements have to be translated into the design of the spacecraft, or basically the control system design of it. See, in bigger spacecraft, normally they go for, it is like equivalent to saying that you are having a flying passenger aircraft. They are very, very well stabilized. They say go with the body stabilized. No, the advantage of it is that you can have a large number of solar cells pointing towards the sun. Then you can have the lot of power being generated. But then what happens is that you correspondingly you will have the problem of management of the thermal thing also. And if you want to stabilize this thing, you need that stabilization problem is also there. But then you need, it is okay for the larger designs. But when it comes to smaller design satellites, what happens? One of the easiest thing, what is this thing is, you take a small satellite, the whole thing itself, you just start putting it in a kind of a spin. See, we were discussing the rotating objects gives you some amount of stability. Use that principle so that you can, whole body is a kind of rotated, and then you are having that kind of a stability which is coming from respect to disturbances that are taking place. So this is how. Then other advantages is you don't have, you get some amount of stiffness, and you need at least half of the solar arrays number of cells is going to see the power, see the sun and generate power, and then you don't have that much thermal problems and other things. But the problem is that when the satellite is spinning, you need to be looking at that which way that the antenna is going to be looking at. This is another problem that what you have. See, with respect to the, when you are adopting this particular most of the small satellites will go for the either the spin stabilized and things like that. But there are two ways of doing it, either depending on the, that's why I brought in the shape and size part of it, and how the mass is getting distributed on the thing. See, in this particular configuration, let us say this is something similar. If you want to compare your 2U satellite, the 2U satellite will be like this, but the 2U or 3U will be like this. And if your mass is distributed, let us say in top to bottom, and if you are trying to spin it around this particular axis, it is equivalent to saying that you take that spinning top. In Kannada, it is called ogre, and in Hindi correspondingly there may be some word. Okay, so that the spinning top, what will happen is the distribution of more the angular, the momentum along the particular axis, if I call it as IFS, and the one which is along this branch like IFT, as long as the IFS is smaller than IFT, what will happen is that this fellow is not going to be remaining stable, it is going to fall. And correspondingly, if I spin it in this way, if suppose if we are having, if my all the requirement of the orientation of the stable way that I want to look at it in this way, then it is this particular configuration is advantageous, where I have that the momentum along that the angular the momentum along the s-axis is much greater than the momentum along the t-axis. It is more or less stable, and it may so happen, like for example, uh, even though this is my stable configuration, sometimes the launcher will give you this kind of a configuration when you come out, and using that ability to recover from this unstable attitude, we can achieve this kind of a stability also. For some reason, this is disturbed and I get into the unstable mode, I will get into the stable mode is also possible to do it. How I do it, like for example, there is a spinning satellite, and let us assume that this is a kind of precision, whatever it is slightly getting what we call mutated and processed, and it is not having a stable kind of it. So if I are having some kind of some people use a thruster, some people use electromechanical, you have to create a force which is trying to disturb this momentum axis, and you will be able to restore that thing. So this is, sometimes you keep hearing the word called spacecraft is tumbling, and we have to do some detumbling operation. So detumbling, see, this is the kind of a word, this is action that is taking place. That basically this particular motion has to be changed back to the stable kind of thing. So coming back to the original question, they say that do we need to control? Yes, we need to we need to control. If yes, what to control? Basically, we need to control the orientation, and then comes what is called the how to control. The how to control. See, the how to control has got a different lot of flexibilities are there, and I have the implementation of it. We need all that ingenuity, and you need to have what is available component. See, generally, what will happen? You can have a set of all possible actions which will affect your real world, but you need to do a study and then optimize what is the way that you are to do it, and you need to model. So this is where the, for example, what is the suppose if I apply all these things on a simulation, and it is the model is like expected to give some behavior. If I behavior I compared with the desired behavior, difference of it, I will get it, and then this is how they will try to go, and finally arrive in your machine learning. I think this is what people will call it as something like that. I am trying to uh, learn because I'm going to teach that in the artificial intelligence terms. This is the computer is trying to learn that this is the kind of thing that either it could be supervised learning or unsupervised learning. You can implement it depending on, but on the ground before you design all things, generally what happens, if I know what is the kind of disturbances, what is going to each one, I put it here, I try to model what is the expected behavior at given that, how I am going to do it. So this is the thing, because I do not want to leave everything on the spacecraft, because a bigger spacecraft, longer duration of the management, and if I have money and all those things, I can implement all those machine learning concept on its own. It will try to learn, and where I cannot have direct contact, so it has to learn by itself. But whereas when I design a small satellite which is going to be having a contact with me too often, then I don't have to complicate all these kind of things. I can go for a simplified. But when you try to do this kind of thing, what will happen is See how do I see? I have seen in this case there is a desired behavior and then comparison with the actual behavior. So how do I know whether it is whether it is going correctly? See, for example, you would have all got into saying that no, many of times a simple thing is that you try to have the pendulum mass, and then many of the practical systems, the control system people or any of the instrumentation people, you would have modeled it as a mass, and then the spring, and then the damper kind of a situation. So when I want, let us say that at given point of time, I am trying to force, I apply a force. If I apply a force into this one, how the system is going to change? See, either it could be like, for example, you are expecting it to get compressed and keep quiet. So you are trying to the thing, but naturally the spring force, what is happening? It will try to have an opposition and try to, and then this the amount of damper mean that basically let us assume that you are having a fluid damper, and that is also going to have a resistance. So the mass is not going to move in the way that you would like to move. So the way, depending on this kind of whether you are trying to have a what the spring constant and you are having this, I think you will have a different response. See, this is, for example, typically my desired response is 100%, but sometimes I do overshoot. I will go above that and try to do this. After some time I will try to settle, but some other point, like for example, I would do, if I design in such a way that whenever I give an action, it just goes and sits there. It is like equivalent to saying that now you get into a lift, passenger lift, you press that particular floor button. You are not if the lift is doing this type of motion, you will never like it. But if I want to go to from third floor, I want to go to fifth floor, after that when it comes to near fifth floor, I should reach fifth floor. I cannot go to seventh floor, come back to third floor, come back to this totally not allowed. And the same way, there are some ways, like for example, if the lift doesn't even go to fifth floor and stops only at the fourth floor, that is also not required. That means what I tell is that it is not at all doing its job. So they, similar to that, I want to have a rotation about 5 degrees. How I do that 5 degree? I want to make at the end of that, at some point of time, it should reach 5 degree rotation from the whatever the direction that I'm giving. So that the how you design the control system, this is where we have the control laws which are coming into the picture. How, which kind of how do you adjust this kind of parameters? You need to know about the spacecraft mass, how this thing. You need to know what is the kind of how, what is the weight, whether it is a magnetic torque. We are trying to do that, because when you put a magnetic torque, people would have known that it has got that so-called the BH curve. There is, you cannot, after some time the response gets saturated. Whether you are in a linear range, whether you are in a saturated range, you need to know matter. And then they, for example, even that motor, whatever is that motor has got a maximum speed beyond which you cannot operate that motor. At the same way, at low speed, the motor will not try to start. You need, let us say, equivalent to saying that people would have traveled in that railway bogies. When you switch on the phone, your fan, it doesn't start on its own. Some people go with that some stick and then try to rotate. That means that some point, for some reason, it is just not starting. What we call in the, especially in the space related thing, when it's at zero speed, what is called the static friction, we call it as stiction. The stiction is playing a lot of role with respect to, because the lubricants and all those things, it doesn't give you that type of mobility. So this is this characteristic that what you need. You need to understand all those things and then try to design the kind of a system. So okay. So now, having done that, so I just want to give an overview of how we want to think. We have a control law which is implemented. See, it could be either the control law means it is either, it can be you have to disturb according to the whether my response is according to the how much I want to go, how fast I have to go, and then what is the settling point, how this thing. This is the kind of a law that I try to implement. We can set up equations that is in that, and then you choose the actuator, and depending on the disturbance, the spacecraft is varying. So this is the way that it is saying that. So I just want to give another example for that. What is that so-called thing? So you look at this particular thing, and let us say that right now I have an automobile which is running at 46 kilometers per hour. That is I want to change it to 50 kmph. So, but the sensor will have its own linearity and non-linearity. Though it is 46, it will not be measuring 46. Let us assume that ideally it is measuring as 45. So I want to go 50, 45 is showing that. So I need to go 5 kilometer faster. So that is the error that is given to the controller. That means that whatever the flight controller or the your onboard computer which says that is the controller. See, then depending on that, what you are using it. In this case, like for example, I need to give the more accelerator pedal. I have to move. So in this case, I have to move by certain degrees. Because again, it is again the calibration part of it. If I move 10 degrees, probably it will match that particular thing. So this is the knowledge that what you this thing that you have to understand this particular knowledge before you apply this whatever the controller it is trying to do that. So this one of the example that what you give that. So summarizing that, based on your ingenuity, based on what is the requirements, you come up with different control laws. So you each and every segment, if you are putting a sensor, how accurate the sensor, what is the sensor characteristics, we call it as everything, any natural things, what is it, it has got its own natural resonance frequency. And whenever you put it in the kind of system, what is called a control system, people, if you have somebody as a thing, they say what is called the bandwidth. See, it will respond only to certain frequencies. Below that, it will not respond. Above also, it will not respond. So, what is the bandwidth that it is trying to do that? So, see, all these things is a kind of interplay. That's why we said that in the beginning, it is an interplay of all these kind of things which will make your satellite a success story. Okay, even all those things, if I go back to this particular example, okay, if I do everything now, how would I but will it be successful all the time? There is one question which I not answered. How will it be successful? Well, I designed and everything. Will it be all right? Will it be an universal solution? It is like, for example, we all take medicines, and medicine, it has got some people have some side effects, some people don't, and it is all general. So the question is how well we are prepared. So that is where we have to do. The question is then comes, what are we there? Can we have the human beings in the loop? A satellite could be a simple attendant. You cannot remove the role of the human beings, and if you are trying to, because there are certain things which is not designed yet, but the spacecraft is undergoing. So you need to have, and sometimes during the development program phase itself, you would have identified certain limitations. You would not know how to overcome the limitation. Okay, so then you will fly it and say that you will see when it happens. So there is a standard phrase is there, in English. I will cross the bridge when I need to. So that type of thing is because you have scheduled. Because as in the beginning, the first inaugural session, somebody told that satellite has to be finished within that 6 months. Okay, you go through all these things for certain things that you have not planned for, you have not done it, but you see it on board. What happens? So now sit down calmly, do whatever you want. What is the flexibility that what I have? Can I overcome the situation? That is why we have that whole role of the human being is very much as the how well you are overcoming the problem is the one which is going to be success to the mission. And also successful mission operation gets you the project fund for the first. So you need to be really successful. Okay, well, I just, what is that thing? What another normal? I don't have a normal procedure. What is it? And because, as I told you, you need to do a lot of programming. Even that after that also, what to program, how to do it. So that everything is well written down. Because one of the things that about the space operation is that it has to follow a high degree of documentation. If it doesn't follow the documentation standard, you are likely to end up in error. And see, one of the thing is, as I mentioned, it is the axis definition, unit definition. See, if you are using a standard SI units, please be specify what is the SI unit. And if if your mechanical drawings of the thing, if it is, like I say, it is following a right-handed coordinate system, you follow the right hand, because you give a diagram for manufacturing, and if it comes with a different this one, then you will have it. So, and depending on the tolerance, everything has to be properly documented and followed up. So this is one of the things in how they, for example, even everything is sent, but regular operations, this is how the typical normally things happen. How do you do that? See, here is what happens. You are supposed to do certain operations. You are supposed to enable certain things on the board. So it is one of the examples that just going through. I will share the slides with Dr. Sudarshan, so you need not to bother about each and everything. But generally, it says that you are doing certain operations. There are certain prerequisites that have to be verified from the telemetry, and then depending on that, I think suppose this is a kind of telemetry that what is the prerequisite verification. These are all the parameters which are see. There is an engineering parameter which you will know that, but correspondingly, what will happen is that there will be code. In this code, if it appears, then you know that this is the kind of this one it is sitting there, desired energy. So if it is there, then this particular color, the so-called the orange color, what it says that I have to do certain switch on, switch off kind of an operation. So that particular thing at this moment of time, the corresponding code I have to send it to a telecommand. And then the yellow, if I have taken the convention that it is happens to be what is coming from the telemetry. So the interactive of the telecommand and telemetry, and then going through a particular sequence, so that I know that things are happening well. So then what is the output? If I look at the particular data, what happens is this is basically, for example, there is a sensor data which is supposed to be the roll data and supposed to be pitch data. And this is I want every particular time frame at some periodic interval. Let's say here in this case, every 5 minutes, something has to happen. See, you can if you see that. See, I am giving some kind of a change in the wheel speed, so it just goes sits there. And there is, you see in the control law, if you look expand and see that there is a slight overshoot is there, then automatically the thing. So the how much overshoot I can tolerate. So that is the kind of thing. And then this is correspondingly, if I have this operation, how much is the attitude is getting disturbed. See, in this case, particular example, I am getting an see 0.04 degree kind of. That means now something about 40 millidegree is the one that whatever changes that it is. If it is tolerable within that thing, you do it. At some time, this itself is something intolerable. You may have to tighten that. And what you see in this kind of instead of why it is not having a smooth waveform, if you look at it, there is so much noise riding on that. So that is the sensor. Not only senses the background, because it is some of the physical phenomena when you transfer to electrical domain, there will be what is the inherent noise will be generated. How well that you are filtering out the noise. Here, for a simple reason, if you are used to looking at the data, you will filter out this noise. But if you are passing through a computer algorithm, you design a filter, and then correspondingly it will remove all the things. But a simple filter is that you have that like what is the successive approximation. If you put a successive approximation, you will be able to see that this is the kind of a thing that what is sitting there. So this is the kind data. What is it? See, there's some other procedure will say that I have to rotate the solar array, something like that. So over the years, you would have accumulated, or you were just saying you were the mission, you would have accumulated valuable experience in utilizing the optimal use of resources. These resources, how well you are doing it, that is where see certain of these resources available only on the ground. See, for example, in the first day, somebody asked a question, why we have to use the C programming and why not any other programming language. Okay, you are used to certain programming language and you will declare, say, for example, ultimately I have to implement that in onboard computer. The onboard computer will have a certain word length and certain data. You cannot have infinite word length. So but on the ground computer, you may have a 64-bit computing. You can declare that a particular variable as an integer or a float or whatever it is, to whatever precision that you want. But you will not be able to do that on board. On board will have something like sometimes you have to declare it, even though it is a float variable, you may have to declare it as an integer variable, because that is how you don't have much flexibility there. So if you are doing it in integer programming where it is supposed to be a float related programming, what you will have is you will have something equivalent to some the truncation errors or something, the approximation errors are going to come. These approximation errors, if it over the I will do it consistently for so long, it accumulate in one undesired. We have experienced this thing, but these are all the things that it has to come out in the ground testing. You design an algorithm that algorithm has to go through your simulator, and number of cycles. Say for example, I am putting it for 1 lakh cycles. In one case, one of our case, in 1 lakh cycles, 99,900 cycle, it introduce a polarity error. So that if it is not known, and some other time what would happen is that when we wanted to move the spacecraft, I'm talking from experience. When I wanted to move the spacecraft, it moved, but it produced a certain thing. It onboard computer went into some hang state. Later on, we came to know that that particular segment of the program was not given enough testing on ground. I have done something with thinking that these are all something that it has gone into that particular. I can do. I have afterwards we can do a postmortem, but at that time, what you will find is you will start seeing that response is not in your desired direction. So you have to be live with that particular situation. So this kind of the value experience, how much you will for here. This is another example where where I want to do a non-standard operation. There are something similar. It is all given there. Look at the telemetry. Look at this one. What I want to highlight is one of the conditions of what I was using the procedure. If error, the previous data you have seen that there are some errors are within the limits. If errors are out of limits, discontinue the operation and get out of that particular mode of operation. So that is the kind of this one that you are. So why the ground with all this kind of expertise, I'll be able to do that. But what happens over the years? Can I share it with onboard? I have now done that. I have learned that everything is there. If this kind of an error, how do I know? So you get a mixture of I can automate certain tasks on the ground and I can automate certain things on the onboard, which we call as autonomy. So you can just share this, our experience and the way of handling things. Suppose it's saying something. One of the example could be, for example, whenever I switch on that some payload, certain times, that I get it most of the times, whenever we find that because of the disturbance to the way that power is demanded, sometimes what will happen is that there will be a voltage dip. Because of the voltage dip, let us some other status it is giving from on to off or off to on, something like that. So ignore. I can write something that if it's something, don't flash an alarm to the ground controller or ground system, ignore. So that is for now, nothing happens because this is how it is going to function. So if and in real, for example, yesterday when the tracking exercise, see, not the, and also because of the orbital motion of the low Earth orbit satellites, the visibility of the satellite to know what is happening on the satellite, you have very limited time. So most of the task, if you are automated on this one, so it will be very good for you. So the health check of the satellite prior to and after a critical operation or something can easily be automated on the ground. Then you can further do that. So how then you have one as you proceed further, if you know more and more of the satellite and more of this thing, you can get into all those AI or deep learning or machine intelligence. You can kind of share this kind of thing, and you can even modify some of the algorithms possible. So you can basically you can do the extension of the life as space asset. Suppose that is what you would have seen that many a times. Any satellite which is designed, for example, that 6 months, it will live for some 3 years, 4 years type of thing. The recent thing is that you have that Mars that helicopter. They have flown the helicopter which is supposed to be flying for about a few flights only, but it has done so many flights. So that means there. See, one is that the amount of margin that they have on that particular system. Second one is they have understood, they have modeled it for such a way that they can adapt to that situation so that they can extend the life of that particular space object. So this is the kind of learning that what you get it. Okay. So overall, now I have tried to address to you what constitutes a satellite subsystem, what constitutes why do we need all those kind of thing when you say that there are so many sensors, actuators, etc., why do you have all those things, some principles of that, and why and how do we manage all these situations and this one last subject which I briefly touch upon that maybe next speaker will be able to do that better. See, and whenever you connect these kind of subsystems and everything, there are some standards are nowadays coming into that. See, computer people will know that there is a series connection, and there is olden days there used to be something like you have RS-232 connections and things like that. Now you have people are talking about TCP/IP packets and things like that. You have that so many, and even for our charging, the earlier it used to be a normal. Now you have the uh, C-type charger, USB 2.0, USB 3.0. You can flip and then do whatever you want. So there are some standardization which is all coming into picture. So let us learn all those standardization which is going to be, because there are some things which are useful. Why? In the sense documentation becomes easy. Second one is everybody knows what they are trying to do. Okay, and very important thing is so-called the grounding of this particular system, because the reference for the satellite, whatever the voltage or something, and diagrammatically I can say this is the ground potential. But how do you ensure on the ground, which is in the satellite which is in the space, which is having a ground potential of 0? So you have to now decide where is the ground, electrical ground which is sitting there. So then I have briefly touched upon what is the EMI protection, and second one is the radiation protection. See, some of the electronics which are the thing, it will experience some amount of radiation damage depending on the kind of quality of the your components. It just varies, because if you want radiation protection, you need to go through a lot of testing. It's slightly become costly. So that's why people will say off the shelf, I think, and do the radiation protection. Radiation protection is nothing but they try to put a shield over it. So that involves a mass, and then that involves a certain amount of thermal management, etc., etc., and that you all have to do that. So see, in this case, some of the slides will tell you that okay, in this case, there is a power line, signal lines, and this particular configuration is there. In this one, you have this is a general. So if you look at, there is a data bus which will be there. See how there is a what we call OBC, the standard bus structure. Nowadays there is what I call, there is a standard which is called the 1553 bus, something like that. You don't directly connect, and there is something bus controllers or something available there. So you go through that particular literature, you will know that there is how do we connect this kind of thing. So it is the bringing up the modularity, and then see whenever you try to look into the literature, I just wanted you to alert there are certain standard terms which you can Google and then get it what is what nothing. Okay, so the this one last slide for me is that what the physical versus ideal system. Whatever you do it, the selection of the materials, selection of the processes, and what are the constraints in which that you are operating, and the applicable standards. All these things define the quality. And again, when it comes to the you everything you have done it, but unless you test it properly, you will not be able to do that. See, as I told, this is thermal testing. Why the thermal testing? What somebody would have already briefed you also. The thermal the ring of the organization. Okay, what a vacuum, you know that. See, at vacuum only certain of the high voltages play havoc. So you have, and then if you are trying to do certain critical things, your payload is having some critical alignment. You try to align it in this gravity field, but you are expecting it to work without any disturbance on the space where the gravity effect is different, or people call it as microgravity. So how do we test it? So you have to create during the testing phase itself some kind of an zero gravity or microgravity, then test it and do it. That is why you will see that some of the astronaut training and all thing, they try to do that extravehicular activity. First practice it inside a swimming pool. So that means that buoyant forces try to cancel out that this particular thing. And the question is the number of samples. How many samples that you will use it to qualify your thing, or in this case, in a kind of a simulation, how many runs that you will run to know that your desired results are ensured. So this is the kind of I just wanted to alert with you. Okay, and just with that, I will try to conclude my session on this particular. Now, I just wanted to give you an explanation, and I have just attempted to just put a drop in this colorful arena of space application. That was my attempt, and my objective was that Now you have to give me whether whether you are enthused or not. And I just wanted to thank especially Dr. Rangarajan, Dr. Jaykumar, and Dr. Sudarshan, and many of those capable people whom I have not met, who are in the audience. Uh, Probably, and then all those people I would like to thank for the opportunity given. And also, I just wanted to, by way of my expressions or the choice of color in the slide on the or the the tone of my presentation, if I had hurt anybody, I sincerely apologize for that. And finally, I would like to thank the institution which gave me the license to talk about space, that is ISRO. Thank you.
Very good, very good. Perfect.
Yes, sir. Thank you very much. So, we will have question from the audience participants.
Good evening, sir.
Yeah.
Evening, please. Go ahead.
Good evening, sir. This is Vinod. I'm calling. I'm talking from JSS ATN Noida. Sir, a discussion was made related to the bandwidth. It was discussed saying like it wouldn't work if the bandwidth is low or even if the bandwidth is high, and the bandwidth has to be optimized.
Yes.
So, what all the factors will be considering in order to optimize the bandwidth for any of the application in general, sir?
See, when we call, for example, come to the control system part of it.
Okay.
Okay, the control system. What is it? Suppose the response uh, depends on the bandwidth of the controller. Okay.
Okay.
See, it depends on you the step you would have seen that if you are you exposed to control system design generally?
Okay.
See, I just tell you that whatever it appears to be a stable operation. Let us say, for example, generally, if you take a feedback, I have just shown you illustration, which is a negative feedback. So the negative feedback, and then you try to estimate the error, and it's expected to cancel that disturbance, and then try to achieve certain things. But then you have to know. See, you are now trying to do that in an operation. That means there is going to be. I just explained to you. See, the sensor is going to give you data at some time instant. That means it will
Okay.
take a finite amount of time to know what is happening on the, even if it is rotating or even if it is changing the temperature or something. That means there is some finite amount of time involved. And the processing, there is going to be certain amount of time. And
Okay.
then you have to decide that when you are, let's say that your wheel or magnetic torquer or something, it is going to take some amount of time to generate the response. So that means all these kind of things, finally some response is coming. That
Okay.
response should be in such a way, in supposed to be in the right phase, that it is try to nullify the disturbance. It should not aid in the disturbance. So that is what is called try to be in the bandwidth. So this how fast you are trying to do that. So if you have a sluggish response, what will happen is by the time when the response arrives, and it is equivalent to saying that many of times you look at our how the movie people predict, you are expecting the police to be available. The police comes to the scene after that whole event has happened, so it doesn't make
Okay.
any difference. So that is what we call that it is a bandwidth of the system. How far? And the same way, like, for example, you have a structure. Every natural structure, for example, that it is having a natural frequency. If
Okay.
certain disturbance is happening on that one, if you are trying to work with that, it should not uh, amplify the vibration, right? It should no, that means you should move away from that natural frequency and start working on that particular thing. Otherwise, see, you would have felt in many places in practical systems, these kind of things are happening, and which will disturb you. Like, for example, even some when you go near a rotating machinery or a thing, the vibration, your whole body will start shaking, even though you are seems to be very stable. There's something
Yes,
is
sir.
uncomfortable.
Yes, sir.
Okay, this is where the effect of bandwidth comes into picture. What is the response? Your observation to the corrective response should be in correct phase. Otherwise, you will be, instead of cleaning up the disturbance, you will be adding to the disturbance.
Okay. Sir, I have one more question, sir. And also, like a discussion was also being made related to the data types which we might be using with respect to an algorithm. So, in such a in designing of any of the algorithm, what all the factors we'll have to keep in mind while designing the algorithm for the application?
See, first thing, how accurate you want the data to be.
Okay.
See, that determines your what is the length of the word.
Okay.
See, any day, for example, how much precise you want. See, for example, you are trying to compare this, let's say, star sensor catalog or something. Let us assume that you are a cluster of stars, and you want
Okay.
to distinguish between one sensor. You have to be precisely be looking at particular. So you need to have more precision for that particular data point. You variable, suppose if you want to use, suppose a star sensor data, I want to make use of it. So your variable and the precision for that variable has got a different. Uh, Weightage than when you look at that yes or no, presence or absence kind of a sensor,
Okay.
absence type of thing. So it is again a question of that the degree of importance of that particular data point, how much you want to associate with respect to variable.
Okay. 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 Thank you, sir. Thank you so much, sir. Thank you.
Thank you.
Nice question. Next. Sir, most of these control algorithms, they are simple PID controllers.
You can classify them as PID controller. Okay, it's because it's a you can bring it down to PID controller, but there are something like sometimes you in higher when you are having for small rigid spacecraft, this will work, your PID control will work.
Okay.
But if your structure is having a larger one and the structure is having a lot of flexibility, like for example, it is one of the picture I showed was though even though the satellite is small, it just has an observation boom, and then you are trying to fly with one kind of let's say one foil. So you will have whatever you do here, that it is going to have a flutter, the flexibility. So the flexibility at that point of time, that you will not be able to know that how much is that. So you have to do some estimation. So in the control system area, certain things in our example, you can only observe. You don't have direct measurement part of it. So you have to try to do some estimation part of it. So that means correspondingly that you have to your what you call it has to be done in a probabilistic sense, not in actual sense. So the PID, and then the people will say that higher order control system.
Kalman filters.
No, that's why you have so much filters and the thing modeling and things like that are coming into picture. And now in this case, whether it is a supervised learning or unsupervised learning, how much you are having this kind of a knowledge on that, how much weightage you want to give. That's why whether you want to give weightage to the data or weightage to the rate, and what is it? So the proportional, integral, or derivative, how much you want to give weightage. So that is where it depends on that particular thing. Certain things are not directly observable, but you have to do certain things.
Okay.
Sir, I have one more question, sir.
Please.
When it comes to the programming with networking, we basically make use of protocols that is for the communication, and each of his protocol has its own set of standard.
Correct.
With respect to data communication, that is, whenever we send packets from one end, from sender to the receiver, there are different modes of transmission through which we send data from one end to another end.
Correct.
So in this application, what are the features that a protocol should have? That is, what do we expect? Or does it remains the same as with respect to the normal network communication, what we usually see?
In the normal network communication, what you use, either you have that connection-oriented protocol or connection-less protocol.
Yes.
See, whether you have UDP or whatever that you have that TCP connection.
Yes.
That is here. What happens is that it is all internal in the sense. See, this is actually sequence of pooling. Basically, essentially, you pool the states and then give the response. This is basically what you just take the real-time programming kind of thing. So I have a kind of a scheduled look into that. So I look at it. That's why I said I give an example of scanning the port. At given this particular point of time, whatever data that is available, when I look at it, I am supposed to accept it. So I send a query, that a query in the sense that I open the gate, and I am expecting the information only from that particular format. That what is, you cannot expect that, no, you cannot waste. And to that extent only, there is one challenge which is sitting there, and still some universities and somewhere is saying that one of the madam in the first day told that I am a wireless person, how much why it is going. Why not you think of having that wireless protocols putting there? You have that, let us assume that a different type of things sitting there in the satellite. I don't want to connect it through a cable. Why don't you take a wireless protocols and try to
Yes.
implement? Your mass budget totally changes.
Yes, sir. Yes, sir. Thank you, sir. Thank you.
Yes, Professor
Sir,
Gayatri. Okay.
Go ahead, please.
sir, in the PID controllers, what is the best way to get the value proportionally constant?
Again, and I'm telling you, look at that. How far, again, it's the response time. How, see how much you want to this thing, you are trying to tune the PID controller. Yeah, you have to now come how fast you want to go. See, let us assume that I have shown one of the example. I am ready to tolerate some amount of overshoot.
Okay, sir.
Okay, so when I did that means I can I worry about let's say there are certain things that how much rate it's supposed to change. If I change it at a faster rate, I may be introducing certain amount of disturbance to other systems. Is it not? Suppose let us assume that I have a solar array which I am trying to rotate. Okay, how much rotator I can give? See, I have to move at a certain slow speed only. If I rotate faster, my connections may get broken.
Okay, sir.
Okay, so that is another. By the rotation, I should not introduce another disturbance moment on the spacecraft. So I have to define at this point of time. I have to give less weightage to the rate, more weightage to the proportion, and there is no there is no integral there. But if I want, mean that, let's say I want to point in a particular direction where I don't want to have a steady state error, where I have to give more weightage onto the I pattern.
Yes, sir. Okay.
It all depends on which one you want, which algorithm. Basically, what is your mode of requirement? If for pointing has got a different requirement, but simply I lost the attitude, but now I want to know where the sun is. I cannot go in a very, very slow way. Very quickly, I want to go to the sun. So that means I just simply don't bother about anything. I just take the rate feedback only.
Okay.
I don't want anything on that the thing. I just simply go on the thing, rate feedback. Quickly, I give a rotation and go there, that whether that thing is there. Or I don't know anything. I simply want to spin the satellite to make a thermal balance.
Okay,
Then
sir.
what happens is that I just simply rotate the spacecraft. I just give 5-degree rotation and keep quiet. I don't know what is happening. I presume that 5-degree it has rotated.
Thank you, sir.
Yes.
Thank you.
Good evening, sir. Sir, I just want to know how we will provide ground in the space.
It's a good question, madam. But now I want to see what do we call ground? What do we call
Ground is
ground? Where that now, see, with respect to that, you see, for example, in a laboratory, when somebody says, I want to give plus 12 volts and minus 12 volts, how do we give minus 12 volts?
minus 12 volts.
So, you, with respect to that, see, what do you call? You take certain point, which all the things is the thing that, see, in all electrical, let us assume that you have positive connection, negative connections on going to all, let us assume DC connections. All the negatives part of it, I bring it to one particular point. Okay, so then I will have that is my reference point, that somehow I will put it into with certain isolation, I put it to the structure. That means something. So whenever I measure that any value with respect to that particular point, I will say that it is positive 5 volts, positive 10 volts, positive this and all those things. Internally, I will have, once again, I will reverse it and say that it is minus 5 volts. Okay, but then you will hear the term called ground lifting. But whenever there is what I presume as zero, if there are certain voltage builds up during that, with respect to where I have put it into the structure, let us assume that because of that, some charging phenomena, I go through that magnetic storm. So what happens? Some amount of charge buildup is there. Whatever I think that it is 0 volt, it is not 0. It is sitting at 5 volt. So then what happens? All my logic will get also boosted up. This is one thing which you have to experience and do it. And that the grounding is, there are some techniques are there. Please go through the literature.
Thank you, sir. Thank you, sir.
Thank you, sir. Very interesting question. Any other question? Okay. With this, I thank Parameshwar, sir. Yes, we should have more interaction, should guide the team throughout the project. We'll have physical interaction either in Bangalore or Mysore. You are welcome to visit Mysore also. Thank you very much, sir.
Thank you so much. That interaction depends on Dr. Rangarajan and Dr. Jayakumar. I am only outsider as of now. Thank you.
Thank you.
Most certainly, because the very reason we have picked people like Parmeshan Pichimani is so that they are the people you saw the excitement. Now, I'm not worried too much about the content per se, but look at the enthusiasm with which they were interacting, and that is what you should learn. Always the subject matter can be email or by reading the book or discussions, you can get it back. But it's very, very important to have that same passion, and then you can get the mission going very, very well. And that has been repeatedly seen by these people whom we are bringing to your group to help you.
So, thank you.
Thank you, sir.